Next, we're going to talk about the process of barrier tunneling. This is not unlike what we've talked about previously, which is where a particle can occupy or have a wave function that's non-zero in a region that's classically forbidden. In this case, we're saying that that classically forbidden region separates a particle from being inside versus outside of a barrier. So this might represent our potential energy curve. And we're going to define three regions, 1, 2, and 3. One which is inside, one which is the barrier, and the other which is outside. The wave function for such a thing, if it started on the inside, should be relatively easy for us to sketch. It's going to look something like this. It's going to be a sinusoid on the inside. It's going to be exponentially damped. And then it's going to be a sinusoid on the outside. The wavelength out here should be relatively similar to the wavelength in there. This exponential damping gets faster the higher the potential is, and the overall amount by which it's decreased gets less the longer I stay inside this barrier. And I expect the amplitude out here to be smaller just by virtue of the fact that the probability wave, part of it will reflect and come back in, part of it will be damped away, and only part of it will get through. That's the basic intuition of our wave function. And now we're going to solve some math that's hopefully going to encapsulate this intuition. But the basic process of barrier tunneling is where a particle starts out on the inside, manages to squeeze its way through this classically forbidden region because it has an energy less than the barrier height u0, and then it has some finite probability for being outside this barrier region. To say a particle starts out on the left side means that there's going to be a wave function, a traveling wave that's going to look like EDI kx moving to the right. Now in general, that's true, but there'll be something reflected back. So actually in the region of side of 1, I expect my wave function to look something like A e to the I kx plus B e to the minus I kx. This latter part being the reflected wave. In region 2, I expect some kind of exponential damped function. And in region 3, I expect a sinusoid again, except I only expect the right traveling wave, because I started out with right traveling, and I can't get left traveling back here unless it reflects at infinity and comes back. So it'll never happen. These constants k, well, that equals 2m e over h bar, and alpha, that equals 2m u0 minus e over h bar. So how do we go ahead and solve Schrödinger's equation here? Well, we know that psi is continuous at x equals a and b, and d psi dx is continuous at x equals a and x equals b. Those are the conditions we're going to solve.